All right. To start today's session, we're going to look over some electron configurations and orbital diagrams that is representing where um, uh, the electrons will go in the atom. Uh, the first thing we probably want to look at, though, is to remember something that we went over toward the end of the last lecture, which is the orbital filling diagram, the little diagram that gives the order in which the orbitals fill when you're writing out an electron configuration. This is important because remember, there are some anomalies in the filling order where you would expect the next orbital to get electrons as you're going through the Aufbau principle, and you're putting electrons in successively higher energy orbitals as you go on. There are certain cases where you would expect the next orbital to be one thing, but in fact it's actually something else. One of those cases where would be the fact that you would normally expect 3D orbitals to fill before 4s, because generally the higher the principal quantum number, that is, the higher the shell number, the higher the energy. So you would expect 4s orbitals to be higher in energy than 3D orbitals because they're in the fourth shell as opposed to the third. And if they have higher energy, they should fill after the 3D orbitals. But in fact, it's the other way around. The 4s orbitals, because of electron-electron interactions, and that gets really complicated, so we're not going to go into all the details, but because of electron-electron interactions, the 4s orbitals actually have a slightly lower energy than the 3D orbitals. And so 3D orbitals actually fill first. And there are other anomalies like that, like basically anytime you end up filling the p orbitals in a given shell, and you would expect the next electrons to go into the d orbitals in that same shell. They don't. They go to the s orbitals of the next shell up. And only once that s orbital of the next shell up is filled, only then do you start filling the d orbital of the shell that you were with before. And that happens every time. And remembering that could be kind of tricky as you're trying to write out electron configurations. That's why this diagram is so helpful. It's very easy to set up because of the way I showed last time. You just write out the shell numbers followed by the letter designation of the type of orbital. So you just write out all the s orbitals from 1 through 7 is a reasonable place to stop. And then you do the same right next door for the p orbitals, only remember, p orbitals don't start until n equals 2. So there is no 1p orbital. So you start with 2 and line them up right next to the s orbitals for the same shell. And then you do the same with the d orbitals. You just have to remember that d orbitals start with n equals 3, so there's no 1d or 2d, but you start with 3d and then line them up with the other orbitals in those shell numbers. And then you do the same with f, starting with n equals 4. And then you draw these diagonal arrows through the orbitals. And of course, there is one in the book, and there are numerous examples online if you want to Google it also. So you can print one out and have it right over your desk if you want. But if you follow the arrows, you get the correct filling order for the orbitals. And so you notice you go 1s, 2s, 2p, 3s, 3p, no problem so far. But then you'd expect next to do 3d, but that's not what's next. 4s is what's next. And then you come to 3d and so on. And that'll work for all of the anomalies. So that is very helpful to have on hand when you're trying to do an electron configuration. As I also mentioned, the periodic table is divided up the way it is. Well, principally, it's divided up the way it is because of the number of electrons in the outermost shell, or the outermost principal quantum number, which is known as the valence shell of electrons. And the number of electrons is responsible for many of the chemical properties of an atom, like what kinds of reactions does it engage in, what kinds of compounds does it form. And as it turns out, well, when Mendeleev was first laying out the periodic table in the 1870s, he laid out the elements according to, grouping them together according to their chemical properties. Elements with similar chemical properties went in the same column with each other. And it was only later that it turned out that we discovered that the reason those elements have similar properties is because they have similar number of electrons in their outermost or valence shell. And so the periodic table ended up being laid out according to which type of electron would be the last one to enter the atom according to the Aufbau principle. And so groups 1A and 2A, way over on the left, are called the S block because the last electron to enter the atom according to the Aufbau principle will be an S electron, will go into an S orbital, that is, in the basically N shell, that N representing the number of the period. So if you're looking for the element in the fourth period in the S block, the last electron in the electron configuration would be a 4s electron. And there are two groups in the S block because an S orbital there's only one S orbital in each principal quantum energy level. That is, there's only one S-type orbital in any given shell because it's spherical and there's only one way you can orient a sphere in space. And each orbital is capable of accommodating a maximum of 2 electrons. So if there's only one S orbital in each shell, then there can only be 2 elements in the S block going left to right because the first element in the S block would, the element in group 1A, in other words, would end the configuration with S1, that is 1 electron in the S orbital of the valence shell, which will be whatever the period number is. The second element in group 2A, in other words, will have the configuration of NS2 at the end of its electron configuration, N again being the period number. Then we come to the D block. The D block is also known as the transition elements. And this is where the last electron into the electron configuration will be going into a d orbital of the next 2 valence shell, that is N-1. So if we're talking about scandium, which is the first element in the D block in period 4, the last element to go into scandium would be in a 3d orbital because 3 is 4 minus 1. And it's in the D block, so the last electron would be in a d orbital. And in fact, it's the first element in the D block, so that would be 3d1. And the next one over would be 3d2 and 3d3 and so on up to 3d10. You'll notice there are 10 columns in the D block because in any given shell that has d orbitals, there are 5 d-type orbitals. And each of them can accommodate 2 electrons. So that's a total of 10 electrons for the d-type orbitals in any given shell. The P block is the other part of the main part of the periodic table. When you get to the P block, that means that the last electron in the electron configuration, according to the Aufbau principle, will be in a p-type orbital of the valence shell, and the valence shell will match the period number. So that's why we say the last electrons will be NP, meaning N being whatever the period number is, and P representing a p-type orbital. And you'll notice if you count across, there are 6 columns in the P block because in any given shell that has p orbitals, there are 3 p-type orbitals, px, py, and pz. And each of those can accommodate a maximum of 2 electrons. And so that's a total of 6 electrons for the p orbitals in any given shell. So if we're talking about period 3, and we're talking about this element right here, boron, which is what it is, the last electron will be a p in a p orbital. There will be 1 of them because it's the first element in the P block. And the valence shell number will be 3. So it's, oh, sorry, is it 2? 2, sorry, 2. So 2p1 would be the end of the last entry in the electron configuration for boron. If you go next door to carbon, that would end with 2p2, and then 2p3 and 2p4, 2p5, and 2p6. And then if there's 1 more electron, you come back down to the next row down, and you'd have 3s1, 3s2, and then if there are more, then you'd have 3p1, 3p2, and so on. And then when you get to the fourth shell, you would have 4s1, 4s2, and if there are still more electrons to go, you get 3d1 up to 3d10, and only then do you get 4p electrons starting to fill. And then we have the F block down here. If you end up with an element in the F block, the last electrons into the atom, according to the Aufbau principle, will be going into F-type orbitals, and they will be in the shell that is numbered 2 below the valence shell. So n minus 2. So if it's the first element in period 6 in the F block, that electron configuration would end with 4f1, because it's the period number minus 2. So 6 minus 2 is 4. 4f1, 4f2, 4f3, and so on, up to 4f14. Again, there are 14 elements in each row of the F block because there are 7 F-type orbitals in each shell that has them, and they can each accommodate 2 electrons. So that's 14 electrons possible in the F orbitals for any given shell. Okay, that was a quick review of what we did at the end of the last lecture. And so to pick up where we left off, we were about to look at actual electron configurations and orbital diagrams. The orbital diagrams are useful because the properties, some of the properties of atoms, like magnetic related properties in particular, can vary depending on whether the atom has any unpaired electrons or not. And it can be difficult just from a normal electron configuration where you write out, 1s2, 2s2, 2p6, 3s2, things like that kind of thing. It can be difficult to tell from that whether there are any unpaired electrons in the atom or not. Writing out the orbital diagrams like this can show you when there are unpaired electrons and when there aren't. And it shows it graphically and very obviously. So it's not always predictable, or it's not always really easily predictable based on the normal electron configurations. So that's why we care about orbital diagrams. The orbital diagrams are usually written with each orbital being represented by either a square or maybe a line or a circle or something like that. And remember, the electrons, when we draw them into orbital diagrams, the arrow with the half head pointing up would be a spin up electron, or it would have a spin quantum number, or m sub s, of +1/2, and the arrow with the half head pointing down would be a spin down electron, or an m sub s value of -1/2. And anytime you have 2 electrons in the same orbital together, they must have opposite spins. Otherwise, they will not go together. Okay, so starting at the beginning with hydrogen, 1 electron, that's pretty simple. Atomic number 1, meaning 1 electron. Its first electron, according to the Aufbau principle, will go into the lowest energy position available. Since we haven't added any electrons at all yet, all of the positions are available, but the lowest energy position would be the S-type orbital in shell number 1. So that's where it goes. And you designate that there's 1 electron in the S-type orbital of shell number 1 by writing 1s. The big 1 in the front represents shell number 1. The S represents an S-type orbital. And the superscript 1 indicates that there's 1 electron in that S-type orbital in the first shell. And for an orbital diagram, you just draw your little square representing the 1s orbital and put an arrow in it with half a head pointing up. The quantum numbers of that 1 electron would be, first of all, n equals 1, because n is the principal quantum number, or shell number, if you prefer. So n equals 1. L, again, is a number that corresponds to the type of orbital. This is an S-type orbital, and so L is 0, because 0 corresponds to an S-type orbital. M sub L would be 0, because remember the possible values for these quantum numbers. n is positive integers starting with 1 and theoretically going to infinity. L, that is which designates the type of orbital, can be 0, 1, 2, up to a maximum of n minus 1. M sub L can take any value from negative L through 0 up to positive L. And M sub S has to be either plus or minus 1/2. So a lot of these two middle values here, L and M sub L, depend on the value of the quantum numbers that come before them as to what they're allowed to be. All right, so for the one electron in hydrogen, we already established, obviously, it's in the first shell, so n equals 1. L equals 0 corresponds to an S-type orbital. According to the rules for M sub L, if L is 0, then 0 is the only thing M sub L can be. In other words, there is only one S orbital for each shell, because remember, the values possible for M sub L will tell you which particular orbital of a given type the electron is in. And if it's an S orbital, spherical, in other words, there's only one way you can orient a sphere in space. And so there's only one S-type orbital per shell. So there's only one possible value for M sub L, I mean. And M sub S, in this case, would be plus 1/2 because I drew it pointing upward. Really, it doesn't matter whether you draw the first one pointing up or pointing down. Just be sure that if you write the number for M sub S, that it matches the direction of the arrow. For helium, now we've got 2 electrons, and writing out the electron configuration isn't that much more difficult. You just basically take the electron configuration for hydrogen and add one more electron. So that one more electron would go into the lowest energy position available. The lowest energy position available is the other position in the S orbital of shell number 1. So the electron configuration for helium would be 1s2. And you would draw that as an orbital diagram as just a square with 2 arrows in it, but make sure they're pointing in opposite directions. And then electron number 1 for helium would have the same quantum numbers as the electron for hydrogen, because to us it is the same electron. It's the same one that was already there. And the one we're really concerned about, so then would be the one that we added. What would be the quantum numbers for the one that we just added? Well, it's still in shell number 1, so n equals 1 for the second electron, this one here. It's still in an S-type orbital, so L equals 0. And there's only one possibility for which S orbital in that shell it's in, because there's only one S orbital in each shell. So M sub L has to be 0. But it's pointing down, so it has spin down, and that would be an M sub S value of minus 1/2. So you notice, as I said, the Pauli exclusion principle says that each electron in an atom has a unique set of 4 quantum numbers. That is, at least one of those 4 quantum numbers has to be different from any other atom or any other electron in that atom. And in the case of helium, the 2 electrons differ in their value for M sub S. So the first 3 quantum numbers are the same, but the 4th one is different. And so they do have different quantum numbers. All right, or at least the sets are different. Lithium would be the 3rd element. That means it has 3 electrons. The first 2 electrons go into the S orbital of shell number 1, just like they did for helium. And then the question is, where does the 3rd electron go? Well, the 3rd electron goes into the lowest energy position that's available. Now, that second S electron in shell number 1 filled up not only the S orbital for shell number 1, but it filled up shell number 1 also. The S orbital is the only orbital present in shell number 1. So now we have to go up to shell number 2, and the lowest energy orbital in shell number 2 will be the S orbital in shell number 2. So that 3rd electron goes into the S orbital of shell number 2. So the overall electron configuration for lithium is 1s2, 2s1. meaning 2 electrons in the s orbital of the first shell and 1 electron in the s orbital of the second shell. In the orbital diagram, we have a filled orbital for 1s, just like we did for helium, and then that third electron goes into the 2s orbital. The quantum numbers for the first 2 electrons will be the same as they were for helium. And for the third electron, the one we just added, the quantum numbers would be, first of all, n equals 2 now, because this is in the second shell. L equals 0 because it's an s orbital. M sub L equals 0 because that's the only possible value if L equals 0. And again, there's only one possible value because there's only one s orbital in each shell. And M sub s, since we drew it pointing up, that would be plus 1/2. So I've underlined the n equals 2 because that's what makes it different from any of the previous electrons. So I'm kind of emphasizing the fact that for each additional electron you add, there's going to be at least one difference between that and the electrons before it. Okay, so this one had L equals 0, M sub L equals 0, and M sub S equals 1/2, just like the first electron did, but the third electron has n equals 2, while the first electron had n equals 1. So that's a difference. The fourth element is beryllium with n equals 4. The fourth electron will go into the lowest energy position available in lithium. And, well, we only had 1 electron in the s orbital of the second shell for lithium. So that means the next lowest position would be filling up that s orbital in shell number 2. And that's exactly where the fourth electron goes. So now we have, oops, that's 1s and that's 2s. So now the first 3 electrons have the same quantum numbers as they had coming into this. The fourth electron will have n equals 2 because it's in shell number 2. L equals 0 because it's an s-type orbital that the electron is in. M sub L equals 0 because that's the only possible value for an s orbital. And now M sub S for this fourth electron is minus 1/2. And that's what's different from the electron before it. Minus 1/2. And we can do a couple more, and then we'll go over something important, and then we'll do a few more. Boron, 5 electrons. We have filled up the first shell completely, and we have filled up the s orbital in the second shell. But remember, the number of types of orbitals possible in a given shell is the same as the shell number. So while in shell number 1, there's only 1 type of orbital possible, and that's an s orbital, in shell number 2, there are 2 types of orbitals possible, an s and p orbitals. And then the other thing to remember is that, of course, there's more than 1 p orbital. There are 3 of them in each shell that has p orbitals. So we would draw the p orbitals as 3 boxes. The boxes could be connected or separate. I've done it this way, but I start connecting them later, just because it's easier to draw that way. And so the first 4 electrons will go into the same positions that they went in for beryllium. The fifth electron will go into the lowest energy position that would be available at this point, which would be the p orbital of the second shell. So we have 1s2, 2s2, 2p1. The px, py, and pz orbitals are kind of arbitrarily defined. You don't really even have to list them in that order. And they're all equal in energy, so it doesn't matter which one of these 3 boxes you draw that first arrow into. Doesn't matter. You could draw it in the middle one if you wanted, or the last one. And for that matter, the arrow could be pointed down. So you have a lot of freedom there. For the last electron that came in, remember the quantum numbers for the first 4 electrons are the same as they were in the previous example. For the electron we just added, electron number 5, n is equal to 2. L is now equal to 1. L equals 1 means a p-type orbital. M sub L can be -1, 0, or +1, That is, there are 3 possible values for m sub L because there are 3 p orbitals in each shell that has them, px, py, and pz. We usually use those values to, left to right, -1, 0, +1. And I drew this electron in the orbital, the p orbital on the left. So we would normally call that -1. And then I drew it pointing up, so m sub s is +1/2. And the m sub L equals -1. That's what distinguishes it from the last previous entry. Oh, actually, the L equals 1 also. That's different from the previous electron. Carbon has 6 electrons. We enter an important juncture here because for 6 electrons, the first 4 electrons will go where they went for beryllium. The 5th electron will be where it was for boron. Then the question is, where does electron number 6 go? Does it pair up with that p electron that you already drew in, or does it get a separate orbital to itself? And this is important because it gets a separate orbital to itself. That's important because, again, magnetic properties of elements are affected by whether there are unpaired electrons in the atom or not. If that electron paired up with the p electron that was already there, then there would be no there would be no unpaired electrons in the atom, and it would have one kind of magnetic properties. But in reality, it gets a place to itself. That is, it gets its own p orbital, and there are unpaired electrons in carbon. And so carbon actually has another type of magnetic properties. Okay, so this configuration would be given as 1s2, 2s2, and 2p2. When we're writing out electron configurations the way we normally do, as just 1s2, 2s2, 2p2, we don't distinguish whether there are unpaired electrons in these degenerate orbitals or not. But that is where the advantage of drawing orbital diagrams comes in. The orbital diagram does show that there are indeed unpaired electrons. You might assume, since each type of orbital has an even number of electrons, you might be tempted to assume that there are no unpaired electrons. But in fact, there are 2 unpaired electrons. So for the last electron that went in, you would have n equals 2, right? L equals 1 because it's a p orbital. M sub L equals 0 in this case because I put that electron in the center orbital. And again, we usually go left to right. M sub L would be -1 for the p orbital on the left, 0 for the p orbital in the center, and then +1 for the p orbital on the right. So this one I drew in the center orbital, and so that would be m sub L equals 0. That's what makes it different from the previous orbital, or for the previous electron. And m sub s would be +1 because I drew it pointing up. The fact that electrons entering degenerate orbitals, that is, orbitals like the p orbitals and the d orbitals and the f orbitals too, for that matter, anytime you have multiple orbitals in a given shell with the same energy, so p, d, and f type orbitals, as you're putting electrons into those degenerate orbitals, the electrons will fill each separate orbital of that type singly before they start pairing up. In other words, it's basically like we are. We prefer to have a place to ourselves, but we'll take in roommates if we have to. And so they will fill singly first, like they did here. And also, it's important that you save a little bit of energy. In other words, it's a little bit more stable if you have electrons in separate orbitals with the same spin. So it's far more likely that both of these electrons in the p orbitals would be both spin up or both spin down, but not one up and one down. Remember, they only have to be one up and one down if they're in the same orbital together. But if they're in separate orbitals of the same type, then they actually tend to point the same way. And that happens because there's a little bit of stability to be gained by doing it that way. Okay, so now we can continue on with a few more. we get nitrogen with an atomic number of 7, so that has 7 electrons, or in other words, carbon plus 1 more electron. So it's not hard to predict that the next electron is going to go into the p orbital in the second shell that was vacant for carbon. So now you've got 3 unpaired electrons, and the last electron will have quantum numbers of n equals 2 because it's second shell, L equals 1 because it's a p-type orbital, m sub L equals plus 1 because I drew it in the right-hand p orbital, and that's what distinguishes it from the last entry. And m sub S, again, would be plus 1/2 because it's pointed up. Oxygen is one more additional electron beyond nitrogen, 8 electrons instead of 7. So it's going to be 1s2, 2s2, 2p4. In the orbital diagram, 1s is filled, 2s is filled. For the 2p, you'll have one orbital, one of the p orbitals in which the electrons are paired with one spin up and one spin down, and then the other 2 p orbitals will have single electrons in them. So you've filled up the p orbitals in that shell, in the valence shell with nitrogen, and now with oxygen you have to fit one more electron in there, so it'll start pairing up with the electrons in the 2p orbital. And then the quantum numbers for that 8th electron, the one we just added, would be n equals 2, L equals 1 because p orbital, m sub L equals minus 1 because I put it in the orbital on the left, the p orbital on the left, that is, and m sub S equals minus 1/2. So it's pointing down, and that distinguishes it from the other electron in that same orbital. If we add one more electron, we get fluorine, which will have a configuration of 1s2, 2s2, 2p5. Remember, there's a limit of 6 electrons for the p orbitals in any given shell, so we still haven't filled the p orbitals in the second shell up yet. There's 1s2, 2s2, and in the orbital diagram for the p orbitals, that means that now we have 2 orbitals with a pair of electrons in them, and only one single electron in the right-hand p orbital. So the quantum numbers of the 9th electron, the one we just added, would be n equals 2, L equals 1 because it's p orbital, m sub L equals 0 because it's the middle orbital. So remember, m sub L values would be minus 1, 0, and plus 1 from left to right. So this went into the middle orbital, so that would be m sub L equals 0. M sub S equals minus 1/2 because it's pointing down. And then we reach neon. Neon is a noble gas, and noble gases are known for being relatively stable and unreactive. And that's because all of their orbitals in all of the shells are filled. So having a completely filled shells of electrons lends greater stability or lower energy to an atom, and that makes it relatively unreactive. If you look back at helium way back at the beginning here, helium also has a completely filled shell of electrons, the first shell, because the s orbital is the only orbital available in shell number 1, and that orbital has 2 electrons in it. That means n equals 1 for helium is completely filled, and that should also make helium relatively stable and unreactive. And indeed, helium is stable and unreactive. That's why it's grouped with the noble gases, even though it only has 2 electrons in its outermost shell. So helium is very stable. Neon is also very stable because its second shell of electrons is completely filled. It has 6 p electrons, but remember, the valence shell is shell number 2, and in shell number 2 it also has those 2 s-type electrons. So 2 plus 6 would be 8 electrons in the valence shell. That's why it's in group 8a. 10 electrons overall, because in addition to the valence electrons, you have the 2 electrons in the first shell. And so now we have the p orbitals in the second shell completely filled. And again, when you have all of the orbitals in a given shell completely filled, that is all of the orbitals in the outermost shell completely filled, that makes the element relatively stable, and that's why the noble gases are relatively unreactive. Okay, the next element would be sodium. Sodium has 11 electrons, so you essentially have the same 10 electrons that you had for neon, and you add one more. Well, after you've filled the second type of orbital, that is the p-type orbitals for the second shell, you've filled up the second shell completely, and the next electrons have to go into the lowest energy positions in the third shell. So the corresponding electron configuration for sodium would be 1s2, 2s2, 2p6, and all of that is just like neon, plus 3s1. So 3s1 is the 11th electron. This also tells us that sodium is in the fact that the electron configuration ends in 3s1 also tells us that sodium is in group 1a because it has one electron in the valence shell, and it's in period 3. That's what the principal quantum number means, actually, is what period is it in the periodic table. And so if you look in period 3, group 1a, sure enough, sodium. So that's one of the other useful things that you can find from the electron configuration, but we'll go over that in more detail later. For now, I wanted to get through those, and that put us way over time on the first segment. So I'm going to end this here, and we'll come back with the second segment in a few moments.